I'm Michael Feiman, and Peter will present the results of this benchmarking. So please return after this break, because it's meat of this benchmarking, and results will be in the end of this presentation, the second part. So I just start from the outline of the agenda. So I will do some introduction of why we did it, and then which factors apply to multi-user performance. Also, we talk a little bit about architecture for the Spark integration with resource managers. And then I present this Spark multi-user benchmark, which we created to estimate these issues. And as I said, after break, data and insights will be delivered by Peter, and we both will be available to answer your questions in the end. Most Spark production deployments, they multi-user and multi-tenant. And it's very important to understand it as an aspect of benchmarking, because most of the benchmarks is actually trying to benchmark some specific workload, one job, and try to make it faster, right? But that's different from the real world case, where you have a cluster where multiple users running multiple jobs. And basically, there is two goals for the cluster administrator. There is a goal of higher utilization of the cluster. You don't want to waste resources. But for the end user, there is a goal of running your workload faster. So it's very important to understand the factors which affect performance under multi-user and multi-tenant condition, and specifically how it's affected in relations to different resource managers. Because it's to our we think that it's not fully understood by community the role in this of the resource manager. Considers that the resource manager is just providing resources, but the performance is all up to the Spark. But in the case of multi-user and multi-tenant, resource manager and integration between Spark and resource managers play a large role in the overall performance and in performance of individual tasks, as we'll see. So IBM contracted Stack. This is an independent agency, and Peter will talk more about this, to perform the independent evaluation of 3 common Spark resource manager configurations and integrations: Spark on Yarn, and this is a version of 2.2, on Yarn 2.7.3, and then Spark on Mesos, and our IBM Spectrum Conductor with Spark, which has its own resource manager, and but the Spark, open source Spark 2.01 integrated with it. So basically, we using the same cluster and the same version of Spark. The only thing for the Yarn with 2.01 had some issues, so we used 2.02. It has issues with in regards with Yarn integration, but it's minor change. So factors affecting multi-user performance. So resource manager configuration is affecting performance, because resource managers basically define how many CPUs, how much memory given to specific application at that time, how many Spark applications are running concurrently, and that can significantly affect in order of magnitude of the given application performance. From the Spark point of view, there is no much way to control that, except that few parameters like Spark execution memory, which is basically not not talking about that resource management, it's just saying how much this Spark application will need. But when it's come to the resource manager, that parameter is taken in effect by the resource manager when it's deciding all the parameters above. So in terms of the individual applications, so if you're running more concurrent applications on the same cluster, it's meaning that each of them getting less resources per application, so your specific application will run slower. And then also the infrastructure itself, like capacity and bottlenecks, affect overall performance and performance of individual applications. Also, the data scale of the application, of course, affects its, right? So more data you process and it's slower its job, it's obvious. And the job itself, the application itself, depends on its logic, so its processing. So, for example, SQL-wise machine learning or other types of workloads. So when we look into the integration points between Spark and Resource Manager, so here is a picture for the yarn. So basically, Spark has special classes instantiated for specific integration. So here you see that we have a yarn scheduler, right? So extension of the scheduler for the yarn. And that's what integrated with the yarn as a yarn client and request resources to run. And as you know, it's supporting both modes, running a driver outside in a client mode and running it inside in a cluster mode, where the yarn is basically also finding resource and start driver inside application manager. So this type of integration is basically defining how Spark is interplay between Spark and the resource manager configuration. So Spark is basically only telling the resource manager how much memory it will need for executor and how much CPU. And the resource manager directly or indirectly determining the rest, how many CPUs and how much memory each application get initially. Whenever application can release or gain resources, dynamic allocations, and also if the resources can be taken and when from one application to another to do scheduling policy and priority and so on to boost other applications. So basically that's what we call preemption. And also it's defining that how many executors will start concurrently, how many tasks will be executed in parallel, and so on. So it's all resource manager defining. So as I said, there is not many benchmarks which actually taken that aspect of multi-user and multi-tenant in account when doing benchmarking. So we design our own benchmark, Spark multi-user SMB, and this is open source. And it's in GitHub, and you can download and use it. It's open source. In the end, in the reference, there is a link on that. So it's designed to kind of simulate real-time cases for multi-user and multi-tenant. So it's trying to follow the realistic workload conditions when we have steady state and not steady state, and mixed workloads. And also different types of workloads. So what we used there is TCP queries and also machine learning and mix of different types of workload. And also, we want to simulate different tuning and optimizations which can be taken in account, like short running synchronous interactive jobs and long running batch job. Interactive jobs is normally running in client mode, while batch job is running in cluster mode, right? So we want to simulate that and mix of both interactive and batch. And execute it all in parallel on the same infrastructure, on the same cluster. And measure overall performance. So basically, you have number of users running number of jobs. So you have a time when it's all need to be finished. In the same time, each of users has its own SLA. They want their own jobs to be finished at predictable time. So that's two factors which we take in account in this SMB benchmarking. Overall time, and then variety of the between the job run times for individual users. So going into the pattern. First version, SMB1, was more simple. It was just use synchronous and asynchronous, only synchronous workload. So the current SMB version 2 has two workload patterns, asynchronous interactive and asynchronous batch. So in synchronous interactive, we're running TCP DS-inspired queries, short queries from 5 to 20 seconds. We're running them in sequences from the client. The job is the client with one Spark context, and the sequence submitted one after another synchronously. So it's wait for one sequence, one query to finish, and then started the next one. And then the asynchronous workload is a longer running queries and also k-means, machine learning jobs, basically k-mean example. And runtime of this from 30 seconds to 5 minutes. And also, it's not on this slide, but basically we're doing it randomization of the order in which we're running them. So the idea is not to prevent all kind of caching, which Spark or Resource Manager can do. Because, so we want to randomize and mix all kind of workloads together. So from these two major patterns, we got to 4 use cases. So the first one is we just running this synchronous interactive jobs. So all of them multi-user cases, but workload patterns is variations of workload patterns. So the first one is synchronous interactive, multiple users. Second, asynchronous batch. In third one, we mix them both in equal 50-50 weight. And in fourth, we're also trying to test the priorities of the resource manager, basically. So we're saying that our interactive workload has higher priority, but we put in also cap on it because we don't want that when we start in interactive, it's take everything, right? So we want that batch job continue to work, but we want to cap it to 70% for interactive and 30 left for the batch. And to test ability to preempt and ability to resume in full speed after that. And you will see in the second part what result we got for different resource managers. So we go in a little bit to explaining how it's done. So as I mentioned, we want to test both steady state and transitional state. So for that reason, we are running these sequences for different users with offset. But in the end, all users running all the workload, right? So we basically test in this state where the users added one by one, and in the end, when they finish in one by one. Because the transition also bring some additional load on the resource managers. So it's fixed offset, and then each user running query sequences, and you see the numbers there. It's TCP, DS numbers, standard queries. And as I said, we do a random variation of these queries inside each one sequence to avoid the caching and so on. So for the asynchronous batch, it's running in cluster mode. So basically, it's submitting the driver to the resource manager, and then it will be started on the cluster. So the resource managers also need to allocate space for it. And because they run asynchronously, so they overlap. So immediately after starting first query, we start in second, and so on. Right? So they overlap. And, but the idea is the same. The query is randomized so that the sequence of the queries in this asynchronous is also random. So basically, this a little bit about what we expect. So, and how what we measure, what we expect. So, as I said, we want to measure two parameters. One is the course metrics like total test duration, right? So all users run all jobs, how long it took in this cluster. And then we want to go to the individual user's SLA and see average relative standard deviation between different jobs for the user. Because that would be a way to see how predictable is SLA for individual user. So what we're doing here, we're doing combined through output per hour, and then we're doing weighted relative standard deviation. Because the queries in different queries is different, so we're doing this relative standard deviation per each type of the queries, and then we're doing an average, right? Because it doesn't make sense to do the deviation between all queries if they're different. Different in their types, right? So it's done per proper type and then averaged. And as I said, that's, the deviation between individual tasks, individual jobs is very important to predictability. So we want to kind of visualize how it looks so that from the picture is actually understood if you see some problems, because with just tables and numbers, it's not that obvious. So we put it in two axes. So X axis is basically overall time, and that for y-axis is duration of the job. So each job is basically will be one dot on this plan. And on X is the time when this job is starting. And by starting a job, we mean that after the Spark context is instantiated and just before we run the query. So in ideal case, you would be seeing something like this blue graph there. Basically, when we only beginning, it's the first user started to run the first query. And because it's taking whole cluster, so the query will be finishing very fast. Then we add in the users and we add in queries, right? So the time of the individual job is runtime becoming longer. And when all users add it and all the jobs run in full speed, you go into the steady state. And in the end, when they started to finish in one by one, because we started them with offset, right? So that again, the duration of the jobs becomes shorter because you have more resources to run whatever left. So that's basically how it's supposed to run in theory. When we run in this test, we're using 20 users, and each of them running around 80 jobs. Peter has more exact numbers, right? So it's a real multi-tenant, multi-user case. And the variation in the dots is basically showing this detailed per query metrics, while the total time on the x-axis showing the overall result of the finishing all the jobs. Okay, so we have 5 minutes before breaks. Any questions for me for this theoretical part?
Please raise your hands and I'll come with the mic. Or alternatively, feel free to walk over and ask the question.
We can discuss, and in the end will be all the emails and so on. So you can, and we'll also keep a blog for this SMB, so you can also ask questions there.
All right, thank you.
So just don't forget to come back, because the bits, the results will be in the second part. Thank you.